So welcome all of you. In the session of the expert talk, today we are having a very brilliant personality, Dr. G.T. Kulkarni. I'm having the pleasure to introduce Dr. G.T. Kulkarni. Dr. G.T. Kulkarni is currently working as a professor principal in Gokaraju Rangaraju College of Pharmacy, Hyderabad. He has completed his B Pharm in 1992 and M Pharm in 1994 from Gulbarga University, Karnataka, and completed his PhD in 2006 from the Tamil Nadu Dr. MGR Medical University, Chennai. He has a total teaching and the research experience of 29 years and has guided 57 M.Pharm dissertation and 15 PhD research scholars. He has published 165 papers in the various national and international publications. Along with this, he is having the 14 books chapter and the various number of international and national patent in his credential. So the Dr. G.T. Kulkarni is a kind of the shining star in the pharmacy profession. Without wasting much of time, I would like to invite Dr. G.T. Kulkarni for their presentation on a very important topic for the pharmaceutical students. So welcome, Kulkarni sir. Over to you.
Thank you, Dr. Nitin. Now I will share the screen and let us start the presentation.
Good evening, sir, and welcome.
Good evening, sir. How are you?
Very
दिनों के बाद.
Fine, very fine, sir. Welcome, sir, welcome.
Thank you, sir. Is my screen visible?
Yes, sir. Your screen is visible, sir. Please go ahead.
Okay. Thank you. Thank you once again. And let us start one important topic today, that is dissolution data fitting. What, when, and how. The problem here is most of our pharmaceutical students do research on some controlled release, sustained release, nanoparticles, microparticles, and such things. And they do the dissolution. But most of the times, the problem is they don't know which data fitting has to be done in which case. So today in this, we will see some of the data fitting modules which we can use for this purpose. So drugs are usually not administered as pure chemical substances, but they are converted into a finished formulation, drug product or dosage form. And these drug products are meant for delivering the drug either to a local action or for systemic effects. And for reaching systemic effect or to exhibit systemic effect, the drug product has to release the drug. That means drug must be available at the site of absorption as molecular dispersion or as solution. For this, prerequisite is dissolution. As we know from this Sharjal et al., this figure is based on that only. Drug in the drug product or formulation will first undergo, if it is a solid formulation, it undergoes disintegration followed by dissolution, followed by absorption, and then the drug enters the body. Once we do dissolution, maybe by following any method, it may be following USP 1, 2, 3, or by using magnetic stirrer or by using French diffusion cell, anyway, we get some data. So it is a critical attribute. And once we get such data, you can see in this figure, dissolution data is given, but the dissolution profiles, 4 profiles are given. All the 4 are entirely different from each other. Some are showing very slow release, some are showing very fast release. Now in such situation, even such situation can come when the students are doing their research work. Different batches are showing different types of dissolution profiles. Now, how they have to compare these? That is the main question. For this purpose, we must do dissolution data fitting. Without fitting that, we can't compare. In case of immediate release products, there are some methods of comparison like F1, F2 and other things, similarity factor, dissimilarity factor. By the use of ANOVA, we can do the comparison. But in case of sustained release, controlled release, we are going to face this problem. Because here, if polymer concentration changes, then surely our dissolution mechanism may change. So profile may also change. Now, let us see why mathematical modeling. Most of the times, mathematical equation can be obtained which describes dependence of release as a function of time. And this tool is very useful to predict release kinetics before the release systems are realized. This is highly useful in predicting overall release behavior. And for comparison also, mathematical models, what they can do? They are most important for designing pharmaceutical formulations, because when you know the dissolution profile, we can modify the dissolution profile according to the need. Then they are useful. Dissolution mathematical models are useful to evaluate drug release processes in vitro and in vivo. And they are also important to come up with optimal design for new systems. Now, using mathematical models, we can predict theoretically all the factors that are controlling a specific release profile, or all the factors which are responsible for a release profile. Like, for example, we can see here the amount and type of active agent, API, the amount and type of polymers and other adjuvants which are used in the formulation, which have effect on the dissolution, and size and shape of the system. This also, the physical parameter of the formulation is also important in dissolution. So how all these things are going to affect dissolution profile? To understand this thing, we need to develop mathematical models. Some of the commonly used mathematical models, here we are discussing only about CR and SR, controlled release, sustained release products. Zero order, first order, Higuchi, Korsmeyer, Peppas, Higson-Crowell, Baker-Lansdale, Weibull equation, Hoffenberg equation, Gompers equation, Peppas-Salin equation. Many are there. Still, I have listed only few here. So many equations are available. So many mathematical models are available. But most commonly, we are using the ones which are shown in red color. That is Zero, First, Higuchi, and Korsmeyer, Peppas. Now, we are concentrating only on these four equations because we are commonly using them. Let us come to zero order kinetics. Equation for zero order kinetics is Ct is equal to C0 into K0 into T. Here, Ct is concentration released at time T, concentration at time 0, and K0 is the rate constant. T is the time at which we are doing this measurement. So this release kinetics, usually when we get this zero order kinetics, normally we get it by coating a core tablet with a semi-permeable material. Okay, if we do like coating of a tablet with some cellulose derivative, okay, like ethyl cellulose, methyl cellulose, some coating, core should be there for achieving zero order kinetics. And osmotic systems, which are already well-known systems, osmotic drug delivery. Then if device is formulated as a slab, we are going to get this zero order kinetics. And transdermal reservoir systems. In transdermal, we have matrix and reservoir. Zero order will be obtained by reservoir system where there is a rate controlling membrane. Now, when we want to find out or plot zero order kinetics, how we are going to confirm it? That is the question. Usually, for any dissolution data, first what we do, percentage release against time. This curve is plotted. If it looks like a straight line, percentage release against time is a straight line, then we can assume that the release may be following zero order. Okay, but we can, just by seeing the graph, we can predict that it may be following zero order, but to prove it, we need to do linear regression of the percentage release against time data. Okay, and normally we are supposed to get, if it is a straight line, correlation coefficient is supposed to be 1. R square value is supposed to be 1. So, or if most of the times if we don't get 1 exactly, then it should be near to 1, 0.999. If this deviation from 1 is too much, then the data does not fit into zero order kinetics. So here what we are doing, simple, percentage release against time data is taken, regression analysis is done, R square value is found out, R value or R square value. So if it should be 1 or 0.99 or 1.01, something like that. So here we have one table which shows how we have to do this regression analysis manually. Okay, anyway, I am sharing this PPT to Dr. Nitin. Later, it can be shared among the students also, so that they can see this table manually and try to do. Now, let us come to first order kinetics. Here, in zero order kinetics, we have seen percentage release against time should be a straight line. But in first order kinetics, it does not happen. It will be a curve. Now, in this graph, we can see that it is a curve. So, equation for first order kinetics is log Ct is equal to log C0 plus K1T by 2.303. So, log Ct is the concentration at any given time t, log C0 concentration at 0, K1 is the rate constant or release rate constant, first order release rate constant. Okay, but here we have to keep in mind where we have to apply this first order kinetics. If it is a reservoir system, we can't apply this first order kinetics because all reservoir systems follow zero order kinetics. So if it is a matrix system where drug polymer are mixed together, we are getting a uniform dispersion which will be compressed into a tablet or which will be made into a transdermal delivery or any formulation. So it should be a matrix. First thing, if it is a porous matrix, you get first order kinetics. If in any porous or non-porous matrix, if the drug is water soluble, then we usually get first order kinetics. Okay, so by seeing the polymer properties, we can actually predict which data fitting or which kinetic equation may be suitable for it. So no, we are wasting time in applying all the equations. We can confine ourselves. Rationally, we can apply the equation. So here in this slide, we can see it is a curve. Now to make it into a straight line, y-axis, that is percentage of release, must be made into a logarithmic form. So either you can take log of all the percentage release values, or you can plot it on a semi-log graph paper. So usually most often we do is log percentage release will be taken and then it is plotted against time. And the slope value is equal to K by 2.303. That means slope into 2.303 will give us release rate constant. Once again here, graph may be straight line, but to confirm straight line, again we have to do regression. Linearity or R square value should be found out to confirm that it is a straight line. So everywhere, if we want to confirm in dissolution, if we want to confirm linearity of the graph, we must do regression analysis. This must be kept in mind by students. Without that, we can't say where this data fits. Next model is Higuchi's model. This equation, Higuchi's equation, classical equation, we will come in the next slide. It is to describe release rate of drugs from, again, matrix system. Okay, so first order is also for matrix system. Higuchi's is also for matrix system. Here, if the system is reservoir, we should not use Higuchi's equation. But here, use of some software with the help of, by the click of one button, students will get all these. Higgs and Crowell, these, that whether it is relevant or irrelevant. Irrationally, we are applying all the models, but that is not needed. So here, if it is a reservoir, there is no need to apply Higuchi's equation. Okay. So here, Higuchi proposed this equation initially in his original paper for dissolution of a lipophilic homogeneous planar matrix. Like it was an ointment containing drug suspension. Later, he proposed a modified equation which is presently being used, which is applicable to all matrix system. No need for ointment. So this is the photograph of Takeo Higuchi or Tak Higuchi. The equation is F1 is equal to Q is equal to square root of this whole thing. In this, Q is the amount of drug released on time T by unit area. Okay, and epsilon is the porosity of the matrix. Tau is the capillary tortuosity. Here, we should not consider all the capillaries, means the channels, small microscopic channels where fluid will take entry. They are not always straight line. They will be zigzag. If the zigzag nature is increasing, tortuosity also increases. C is the concentration, initial amount of drug contained in the dosage form. CS is the solubility of active agent in the matrix. D is the diffusion coefficient in the matrix medium. So by combining all these things into one constant, F1 is equal to Q is equal to KH into square root of T. So this is the simplified form of Higuchi's equation. All these other things except T, they are put into one constant. And this KH is called as release constant of Higuchi. Now, for applying Higuchi's equation, we have to make some assumptions. That is, the matrix contain initial drug concentration much higher than solubility of the drug. Concentration should be very high. Then we can apply Higuchi equation. Diffusion is only one directional. Edge effects should be negligible. In all the direction, diffusion should not happen. Thickness of dosage form is much larger than size of the drug molecule. It is natural. And swelling is negligible. This is most important. If your matrix is swelling, then we should not use Higuchi's equation. Diffusivity of the drug is constant. Perfect sink conditions are attained in the dissolution flask. So this is valid in case of polymers that do not significantly swell on contact with water. So non-swelling polymers fit into Higuchi's equation. Just by seeing the polymer property, once again, we can make out, like if the polymer is ethyl cellulose, which is hydrophobic, it will never swell in water. So here, Higuchi's equation is applicable. For example, in place of that, if you have gum caraya or xanthan gum, which have too much swelling property, Higuchi equation will not give any result. There is no need to fit into this. Next equation is Korsmeyer-Peppas equation, which is one of the most widely used. And this one paper of Korsmeyer-Peppas has crossed nearly 1 lakh citations. So the equation is Mt by M infinity is equal to Kt raised to N. Mt by M infinity is the fraction of drug released at any given time T. Or in other words, percentage of drug release. Simply speaking, percentage release and fraction of release, they are one and the same. There is no need to once again get into any other confusion. K is a constant called kinetic constant, and which incorporates structural and geometric characteristics of the device. If the device is round, if the device is rectangular, if it is square, what is the thickness of the device? Based on all those things, or what is the porosity of the device? Based on all, the K value changes. N is the release exponent, which is obtained from slope of the Korsmeyer-Peppas equation. it actually, this n value, slope value of Korsmeyer-Peppas equation is actually indicating the mechanism of release. In Higuchi, we will just see if it is straight line, it is diffusion controlled or not. Whereas in case of Peppas equation, it is not only diffusion controlled or not, what is the mechanism of diffusion? That also is told by this equation, Korsmeyer-Peppas. So logarithmic form of this mt by m infinity equation is log mt by m infinity is equal to log k plus n log t. So according to this, if we are plotting a graph of log fractional release against log time, that is log plot, log percentage release against log time. If we do, then slope of the line is equal to n, intercept will give you log k. That antilog can be taken to convert it into k, that is called as kinetic constant. It is not rate constant, it is kinetic constant in this case. So we can see the equation here. One graph I have shown. So from in all these graphs, slope is n, intercept is log k. So calculation here, one more important point which I want to emphasize for the students is when you are planning to plot Korsmeyer-Peppas equation, don't use all the readings, percentage release against time. All readings should not be used. Actually, 10% to 60%, whatever values are there, below 10%, don't use those values. Above 60% also, those values should not be used to plot this graph. Because when in the initial stage, when the release is less than 10% or less than fraction 0.1, drug release is usually very rapid because surface drug is getting released faster rate. Burst release type thing will be seen. So above 0.6 or above 60%, usually it tends to slow down. So here, those points below 10%, above 60% points will not fit into your straight line. That's why, because above 60% dissolution slows down, below 10% it is too rapid. That's why whenever we are planning for Korsmeyer-Peppas equation, just use the values between 10 and 60% only. Above 60 not allowed, below 10 not to be used.
Sir,
So depending on the value of n, we can calculate from any matrix system, we can calculate the mechanism. So one here, this Korsmeyer-Peppas equation describes only two things. One is Fickian model. It follows Fick's laws. Case 1 is called Fickian model. Non-Fickian models are case 2, anomalous case, and super case 2. What are these? Just in 2 minutes, I will explain. Fickian model are case 1, where n value is, slope value is exactly equal to 0.5. And in this case, drug release is governed by diffusion. So if n value of Korsmeyer-Peppas is 0.5, means those readings directly fit into Higuchi's equation. You will get a straight line. Now, here, what is happening in Fickian model? Solvent transport rate or diffusion. Solvent is diffusing inside the matrix. This movement of solvent is greater than the process of polymeric chain reaction. When you are using a polymer, you have compressed it into a tablet. When it comes in contact with solvent, chains will relax, they will open up. Rate of opening up of the chain is slower than movement of solvent into the matrix system. Under such condition, Fick's models are, this becomes Fickian diffusion. Equilibrium of absorption takes place very rapidly because exposed surface of the polymeric system, on the surface equilibrium happens because liquid will move in, drug will dissolve immediately. So equilibrium will happen. And this is actually characterized by diffusivity. D value what we have, that is the thing which controls the dissolution or release here. In case of case 1, that is Fickian model. Case 2, non-Fickian, where n is exactly equal to 1. Drug release corresponds to zero order kinetics. Okay. Case Fickian diffusion, drug release is diffusion controlled. Higuchi's model can be applied. If n is equal to 1, it fits into zero order kinetics. Mechanism of drug release is swelling. Actually, Higuchi's equation is for non-swelling matrices, whereas Korsmeyer Peppas can be used for swelling, non-swelling, any type of matrix system. So, release here is if n is equal to 1, swelling or relaxation of polymer chain. Here, when the polymer come in contact with water, the chain relaxation occurs first. Then drug diffusion starts. Diffusion of solvent through the system is very fast compared to the process of relaxation on gel, vitreous, polymeric interface. Means, I will show that figure also. So here you can see, when diffusion happens, when the solvent enters into the matrix, outer portion of the matrix will swell and it will make a gel-like layer. And inside core is still dry. The water has or solvent has not yet reached there. Okay. So that is the outer portion, that red color portion what I had shown is the jellified region. And inside penetration, once that jellified region is formed, then diffusion of solvent into the system slows down. And vitreous region has almost no penetrating solvent because the outer jelly layer does not allow solvent to penetrate into the inner core, which is not yet wet. And at the end of this case 2 transport, for a long time this case 2 transport will happen. Same thing, slowly solvent will diffuse and this inner core will go on reducing. It becomes smaller and smaller. At the end of this, when all the core has been penetrated by water or the molecule, then what happens? Fast increase in the absorption rate of solvent may be observed because there is no dry portion. Everything is now wet. Solvent will move in faster. In this situation, case 2 becomes now case 2 transport at the end gets converted into super case 2. Okay. Here what happens? The gel, due to expansion of forces exercised by swollen gel in the vitreous nucleus. Here I am showing these black colored arrows because the gel layer is constantly exerting a pressure on the inner core. That is going to become super case 2. This force is too much. Force of jelly region is too much. So this happens when n value is between 0.5 and 1. So here model is non-Fickian or it is also called as anomalous diffusion, and mechanism of drug release is diffusion and swelling. Both are happening together. Diffusion and swelling rates are comparable. Means whatever may be the diffusion rate, swelling rate and diffusion rate will be almost near to each other. And rearrangement of polymeric chain occurs slowly. And diffusion process simultaneously cause time-dependent anomalous release here. In super case 2 model, where n is more than 1, above 1. So this is extreme form of transport. During the absorption, tension and breaking of polymer, here when the outer vitreous layer is exhibiting too much of pressure on the inner core, here what happens? The inner core, the molecules, polymer chains cannot tolerate that shear force, and instead of relaxing, they will break. So polymer breaking will occur. Once polymer chains are broken into smaller pieces, relaxation is fast, absorption of solvent is also fast. This we call as solvent crazing. The polymer has become now crazy for the solvent. It will absorb faster. So outer layer of gel limits this vitreous nucleus, which is, vitreous nucleus means inner dry portion, which is a cylindrical sample which prevents axial swelling of the gel. It does not allow swelling, producing tension of compression on the nucleus. This nucleus will be under pressure, compression from the gel side, which is outside. As the polymeric interface gel vitreous moves to the nucleus from outside, as these arrows become longer, then the tension increases until the nucleus breaks. All the polymer chains which are present in this inner dry portion nucleus, they will break completely. Until then, this pressure will continue. So here in this table, we can see interpretation of drug release from polymeric matrix of different geometry. Means, as I told, if it is planar, like thin films, if it is cylinder, if it is sphere, means 3 geometry are there. So here value exponent, that is n, will be different. So here also anomalous transport and values you can see here. In case of planar, it is different. In case of cylinder, they are different. And in case of sphere, that means here the geometric form of the dosage form also is important. In case 1 transport also values are different. In super case 2, again we can see different values for thin films, cylinders and spheres. Okay, this indicates that we can use this Korsmeyer-Peppas equation for anything. So Fickian diffusion generally occurs in polymeric matrices. This is in polymeric matrices where value of vitreous transfer is less than the temperature of the environment. That is, glass transition temperature is less than environmental temperature. When polymer is in rubbery state, polymeric chains have high mobility, enabling easy solvent penetration. They are rubbery, elastic. It is possible to observe Fickian diffusion in polymers with Tg higher than ambient temperature when a plasticizing agent is added. If a polymer is rigid, if you add plasticizer, definitely it will affect the glass transition temperature of that polymer. That's why if it is rubbery, flexible polymer chain, you can see Fickian diffusion, or else you can make it Fickian. Non-Fickian to Fickian conversion is possible by adding a plasticizer. Non-Fickian processes
we are
are
running
normally
short of
formed.
time, sir.
Okay.
Only the 2
So
minutes.
let us come to, no, this, I think I have explained the mechanism and all those. Now, last slide is summary. We can see here, if we know the property of polymer, we can understand which model to apply. 0 order for reservoir and osmotic systems. First order, porous matrix and soluble APIs. Higuchi, only for matrix systems which do not swell. Korsmeyer-Peppas, matrix of different affinity to the solvent. They can swell, they may not swell. In all cases, we can. Fickian, when polymer is rubbery state or when plasticizer is added. Non-Fickian, except all these, any other thing fits into non-Fickian model only. So, thank you.
All right, sir. Thank you very much sir, for wonderful presentation on how to fitting the release kinetic model in the data of the dissolution. Sir, I am having the one question. Although we are running short of time, I am expecting that you will cover the answer within the fraction of minute or even the second.
Yes, yes.
Sir, what is the good or the right method? Means if I'm preparing any formulation, without knowing what kind of the formulation this is the matrix or reservoir kind of. So I don't know what kind of formulation is. So is it the right method that I am putting the dissolution data in all the release kinetic model?
No, for example,
yes,
when you are formulating, you know what you want to formulate.
Yes.
For example, if you want core coat system, then it is reservoir. So we have to go for, accordingly, we have to use 0 order or something. So if it is mixture of polymer and drug, then it is matrix. Either then in such case, we have to see whether polymer can swell or not swell. Whether the polymer is flexible or non-flexible. For example, some gums are there which are not flexible.
Okay.
There,
bottom line of this, the conclusion of this whole presentation is that it's always better to know what kind of my formulation is. Whether this is reservoir kind or whether this is the matrix type, then only select accordingly the selective model for their release kinetic.
First, we should know the dosage form type. Second, we should also know the properties of the polymer. That's why pre-formulation is most important. It plays a major role in formulation development for this reason only.
Thank you very much, sir. Now I would like to invite
Thank you.
Director Dr.
Thank you,
Dr. G.D. Gupta, sir. Sir, over to you.
Thank you very much, Dr. Saab. I know that time
Thank
is
you,
very
sir.
short because the limitation of the